Okay, you guys, we're going to talk today about orientation mechanisms. So we just got done with our second exam unit. We're now ready to kind of get into more complexity. The first thing that we want to do is go to the very basic of how animals respond to stimuli. So we got to go back to our understanding of modalities. You remember all those things we talked about at the beginning? We have chemo, we have mechano, we have photo. Now we're going to actually see how animals orient in relation to these stimuli. And we're going to go to some classic 20th century work. It all starts with two guys, Frankel and Gunn. And this is 1940. Their particular famous landmark paper was on orientation mechanisms in animals. And I want to break it down as they did to the very basic two concepts. The first one is the word kinesis. The word kinesis refers to motion, and the word taxis, which refers to order. So we're going to look at animals that behave and interact with stimuli. They respond to stimuli in very simple ways. We're going to scale ourselves up to the point where we're seeing animals that are using multiple stimuli at any given time to orient themselves and locomote and perhaps migrate. But to do this, we've got to really build a solid foundation. So we're going to use Frankel and Gunn to build that foundation, starting off with kineses. And I'm going to define this. Actually, over here, I want to lay out some important ground rules regarding stimuli. The first thing I want to mention is that we have non-directional stimuli. So think about a stimulus, something that you detect with your chemosensors or your receptors, and you have no ability to determine where it came from. Odors might be like that. All of a sudden you smell it, but it's not like you can say, hey, you did that, or you did that. And that's a non-directional stimulus. The other kinds of stimuli are directional stimuli. And of course, with directional stimuli, you can determine where they are. The most directional stimulus that we know, of course, is the most energetic one, or the highest energy one, and that would be light, the speed of light. So anybody could sit in a pitch black room and turn on a tiny little flashlight and just see exactly where it is. So as we work through this, I'm going to be talking about non-directional stimuli and directional stimuli. So now we get to kineses. I think I'm going to change this to kinesis and define it. This is response to a stimulus gradient. Stimulus gradient. I think I'm going to underline this because I'd like us to be familiarized with what a gradient means. And then importantly, but the movement is not directly related to it. Of course, it is the stimulus gradient. So that's the first thing. Two different kinds that we're going to see. One of them is going to be what we call ortho, and ortho is going to be change in the rate of locomotion. And the second one is going to be clino. Whenever we see this root, it's always going to mean turning. So this is going to be a change in the rate of random turning. Matter of fact, I'm going to say change in the rate of random turning. Okay. So rate of locomotion, random turning. Then what we want to do is further qualify these things. We want to further qualify these kineses with another set of terms. So the next one would be a direct kinesis, and this one is going to be where the rate that we're talking about, so we have this word rate here, the rate increases with increasing stimulus intensity. Okay, and the second is what we were going to call inverse. An inverse means that the rate decreases. So I'm going to, with increasing stimulus intensity. I want to draw a simple graph that will really show what this means. So here we go. Here's the rate increasing on the y-axis, and then over here, here's the stimulus increasing on the x. Simple graph. A direct goes this way, an inverse goes this way. So we're going to talk about a couple of examples and try to sort this out. Take a look at this. I'm going to show you an experiment in a way. We're going to take a behavioral arena, a pretty simple behavioral arena. Suppose that this is a top view. So this is basically a bioassay, a behavioral bioassay. Usually call these things an arena. So it's some kind of a container where the study animals are going to be dealt with. And suppose that we can create a gradient, some sort of a smoothly changing range in humidity. And I'll use a whole bunch of, I'll try to kind of shade this thing. Let's say that this end of the arena is really, really, really humid. And then progressively we get less humid. I'm trying to show this, I hope it looks decent. Progressively we get less humid. And I could do this with brilliance with the old chalkboards, but so the idea is that this end is very moist. So we have a humidity gradient. This end is dry over here. And it's an arena. Get a couple of scratches in here. And even fewer here. So hopefully this looks like some sort of a continuous gradient from very moist to very dry. And suppose that this is a terrestrial environment, so it's not below water. Maybe it's created of sand, with sand or something like that. And we place an animal in there. And what if the animal does this? We place an animal maybe right here. The animal takes off, and then maybe the animal turns, and maybe the animal runs along here for a while and turns here. It's going a long way up to the point where, wow, once it's getting moist, this animal is still locomoting, but it's turning much more frequently. it walks a lot of steps or covers a lot of ground before it turns when it's in a more dry area. And then, of course, as it gets progressively more to dampness, it's turning at a higher rate. So what I want you to do is just take a couple of seconds and use the words that we just described for kineses. Use the words for kineses and try to figure out which ones we would apply to this. So the first thing is to do, this one's all about random turning, isn't it? So I think what we're going to do, this is about turning, the rate of turning. And it looks pretty random. The rate of turning, so we want to incorporate the root clino. The rate of turning is increasing with increasing humidity. So it's definitely a direct. So increase with stimulus intensity. And therefore we want to use the word direct. And then the other thing is, of course, this is a kinesis, non-directional stimulus, so we got to throw in the final word, which is kinesis. Put all this together, and what we have here pulling all of this stuff together is a direct clinokinesis. So we want to look back on this and show that this is an example of a non-directional stimulus. I mean, how many of you could walk into a place and close your eyes and determine where it's more humid and not? No, we're not that good. Water is moving very fast in the environment, whether it's water in ambient air, humidity, or otherwise in soil-like substrates. And it's not directional in this case. Now, water can be directional if it's flowing down with gravity, right? We'll see that later. Of course, that's a whole different level of order. So, non-directional stimulus. This is an example of an arena study. This animal that did this could be something like an isopod. Example of this behavior, an isopod. If you know what this is, it's a little crustacean. It's a terrestrial crustacean. Sometimes we call them roly-polies. If you guys take a look under the hood of an isopod, you'll see that although it's a terrestrial animal, it has gills. So it has to stay in moisture. Pretty simple animal. And again, because of the non-directional stimulus nature of moisture in the ground, these guys are going to actually have specialized behaviors to get there. And one of them could be, I'm taking a walk to find water, and I'll turn more frequently when I do. And that tends to keep them in a safer environment. Of course, later on, we'll see how you're going to use more than one single cue to end up where you're at. A lot of you might be thinking that isopods are usually spending a lot of time out of the light as well. And so then we would bring in another level of stimulus response to actually get somewhere. But this is where we start, basic descriptions of these phenomena. So there's other kinds of kineses that are out there. An orthokinesis would be, I'm just going to be really fast if under one stimulus condition, and I'll slow down as either it increases or decreases. So I want you to feel how you could use these words. As a matter of fact, maybe you should think about what would an inverse orthokinesis look like. I'm not going to tell you. I'm just going to write this down. So the ortho is referring to rate. Kinesis is, of course, the nature, non-directional stimulus, and then inverse. The rate is decreasing with an increase in the stimulus. So take a look at that. So that's the first level that we want to deal with. It's going to get progressively more interesting as we get into different kinds of stimuli and different kinds of receptors that respond to directional stimuli. Also want to remind you something that we talked about a long time ago that was pretty amazing. So, little star, remember this, bilateral symmetry. So we talked about bilateral symmetry in animals. That means left and right. And of course, I think I did an example. I told you guys to close your eyes and then I threw a pen or something and it bounced off a certain part of the room. And all of you could detect the direction of that sound because you've got you've got a phonoreceptor on this side of your head, you've got a phonoreceptor on this side of your head, and if one of them gets more stimulus than the other, more action potentials. Remember all the good stuff, the types of summation that we talked about. But if one of them gets more stimulated than the other, directionality is there. It's all it takes. So we're going to look now at directional stimuli, and that's going to bring us into the world of taxis. So taxis is the plural of Franklin Gunn's next level of orientation mechanisms in animals. Taxis, I'm going to put here, note, taxis are two directional or associated, let's get this right, directional stimuli. And we'll take a look at them. There's going to be 4 types that we want to deal with. The first one is called clino. Notice that we already talked about this root, clino, and it has to do with turning. More on that in a minute. Clino is where you only have one receptor for whatever the stimulus is, and it's basically the bending of the body that enables the animal to sample through time. So one receptor, this is called, so basically, bending back and forth is kind of the idea through time. You think about it like some imaginary animal that has a big trunk or something, and you can move it over here, take a whiff, move it over here, take a whiff, or whatever. That's an example of sampling through time. I'm going to pull out a color and remind you that if you are doing this, we call this sequential sampling. And the other thing we want to know, if it is sequential, for comparisons, there has to be the ability to compare. So this is going to require at least some form of memory. In order to compare the second sample to the first, you're going to have to memorize or remember the first sample reading. So we have complexity of systems here as we work our way up. So that's clino. The next kind, so I guess we should call this clinotaxis, right? The next kind, I'll go up to the top. Use my board resources as good as I can. All right. So the next one, continuing the list, is going to be tropotaxis. So tropotaxis is going to be what we call, we're going to use 2 receptors. And because of this, both receptors, like your ears, are going to be monitoring or responding at the same time. So 2 receptors, we're going to call this one simultaneous sampling. So two receptors simultaneously recepting. And the general response here is to kind of maintain balance. I mean, you can imagine maybe an animal that is flying at a certain time of day and maintaining a particular balance between the left and right for this bilateral symmetrical animal to kind of go and keep a line. That's an idea of what tropotaxis is. So I guess I should remind you that we tend to associate this with keeping a balance. And that's how tropotaxis is interpreted. The next one is special. So C, in terms of taxis, is what we call telotaxis. The word telo is goal. So this is all about a goal. Goal-directed. This is special. I'll put a star here. This is a special case. Telotaxis requires what we call directionally sensitive receptors. And we only know telotaxis as a response to light. Because the great directionally sensitive receptors are eyes. The next one is pretty cool. This is called menotaxis. So menotaxis is orientation at fixed angles. To the stimulus. So I'll give you an example of this one. A lot of animals, especially nocturnal migrators, are flying or walking, whatever they're doing, at a fixed angle to the moon. This is kind of crazy. You've seen this before. You might not know it, but if any of you have ever walked around on a hot, humid summer night somewhere, and you look up at the street lamps, you'll see a lot of insects kind of flying around. Well, these guys are menotactic. They're actually flying prior to mankind throwing all of this horrible array of tiny little fake moons all over the place. Prior to that, these insects were able to use the moon as the one source of reference to fly at an angle to achieve a locomotion, to achieve a directional. And we have all these false moons, and things get kind of screwed up, and they fall at a fixed angle and eventually spiral into the lamp and hit it and fall to the ground, those kinds of things. When we talk about the sea turtles pretty soon, I'll bring up the example of little baby hatchlings that come up, and they're using a multitude of sensory cues. They need to get to the ocean, right? But what about all of those Florida houses and all that light that Americans especially place all over wherever we live? This guy comes up and does a kind of a phototactic or menotactic response and goes the wrong direction. A sea turtle hatchling that goes the wrong direction is definitely dead. I mean, it's high stakes enough just to get from the nest to where you came out, down the beach to the ocean. So this is a good things are coming our way. We're going to study some really, really cool behavioral phenomena, but this is the substrate of it. So the next thing we want to do is after identifying these 4 major categories of taxis, what we want to do is discuss taxis from a modality-specific rating. So taxis can also be categorized based on modality. And the modality concept, we're going to get really specific here. I'm going to show you the different kinds of taxis that we have. We have, of course, phototaxis. We have chemotaxis. We have hygrotaxis. And I just got done saying you can't do that, but you can. Hygrotaxis, mechanotaxis. Both of these, well, hygro is really a specialized chemo, isn't it? And then we could go with anemotaxis. This one you don't know, so I guess I would give you a little more information. This would be wind or breeze. These guys you do know, so I'm not even going to give them to you. Rheotaxis is a category. This has to do with stream. So moving water, of course, is an opportunity for rheotaxis. And then scototaxis, this of course would be for dark. And then phonotaxis. Phonotaxis would be for sound. You guys might see that, hey, wait a minute, you already said phono in the form of mechano, but this one here is a little bit more specific. So there's several of the different kinds of taxis that, that we can have. The next thing we need to do about taxis is discuss positive and negative. Okay. So taxis are either positive or negative. So positive is towards the source or to higher concentrations. Concentration, strength, etc. And then negative would be away from. So away from higher concentrations or strength. So now we have these things happening. It's very, very common. A lot of insects that come out at night. Here's a cockroach. A cockroach is out in the middle of the night feeding on some of the scraps that were kind of brushed off the table, bits of bread, this and that, and you go for, I don't know, a late night kitchen run and turn on the light, and the cockroaches, they go jetting. They're negatively phototactic. Of course, they have a lot of other things too. I want you to think about using these kinds of terms to describe the response of cockroaches that was depicted in the neurological studies. So remember, we have the 2 backward projecting sensory structures full of little hairs called cerci. And if we puffed air on a right circus, the cockroach went forward and to the left, away as much as possible from the source of the most intense stimulation. So do that behavioral response in these terms, because it is a form of taxis, but I want you to pick out which of these words work for the cockroach escape response and which of these words work, and then stick taxis there. So this stuff is building. All right. I have no intention of having go. Damn it, Roger. Okay, sorry about the interruption. Anyway, what we're going to do now is we're going to put these things together. This is death by mosquitoes, not in the disease sense. I know that I've given you guys a lot of mosquitoes, but this is what I do, but we're going to get out of it. This might be about the last thing that we do with mosquitoes until we do some sexy stuff at the end of the semester. So we're going to take a look at a system that we're familiar with. Everybody knows the olfactometer because it was just on the exam. So I had a fancy diagram of it in the exam. This one's that straight top view, so we had this kind of thing. This is how I drew it on the board the first time around. So this was the flight tunnel, this was the release chamber. Of course, we had a door that would swing open. There was a fan here that moved air. Then I had drawn these funnel traps like this. And then a split chamber here. I think we put honey on one side, we put a bird on the other side, and then we have this thing, which is kind of where my airflow came in. And that was purified and humidified air. So right here is the key, but the other key is right here, airflow. Airflow through the whole thing. So here's air that's cruising through, moist, purified air, cruising through. Of course, this air is going to pick up some of the nectar odors from this side. That's going to go through the trap. Then we're going to have picking up bird odors. That's going to go through the trap. And then, of course, this air is just going to hopefully flow in a very straight, laminar way through the flight tunnel and ultimately out the back. So think about the kinds of things that are present. In the air, we have H2O, because remember I said that it was humidified. So H2O, I just gave you the root hydro or hydrotaxis possibly. We have in the honey, we're going to have these things that are essential oils. So I guess I'll use the word volatile essential oils, chemicals that could be attractive to mosquitoes, things that could bind to specific receptors on the antennae, and of course if everything works well and thresholds are exceeded, there's a signal. On the bird side, we're going to have CO2 above and beyond the baseline level that is present in the regular air. We're also going to have other things. Well-known mosquito attractants, or attractants for mosquitoes that come from vertebrate animals would be lactic acid. Let's see, the other one is octanol. These are two famous chemical attractants. But then beyond that, remember that temperature. We've got that phenomenon going on. Mosquitoes respond to that. And then beyond temperature, we have vision. We put all of these things together, and we've got a whole bunch of stuff happening. Now, vision is not really part of this. Technically, the mosquitoes flying in this apparatus can't see the bird, but definitely temperature could be radiating more so from this chamber than this chamber. Octanol and lactic acid are coming out, and the idea is that a mosquito that comes out of here, a mosquito that comes out of this release chamber, I think I need to get a better color. A mosquito that comes out of this release chamber is technically going to fly upwind, and here is probably the key. This is the decision point. Somewhere right in here, this mosquito is going to be detecting honey, the odors associated with, but also going to be detecting bird and the odors associated with, as well as the other stimuli. And here is this decision point. This decision point, and as we found out already, if this mosquito had spent the first part of its life feeding on nectar or feeding on sugar in a laboratory, remember ad libitum feeding, if this has happened, this guy is, this female mosquito might end up kind of working this way, and boom, stuck in the trap. bird response, positive bird response. Remember the other population of mosquitoes, maybe the ones that were starved, do the same thing, and they fly upwind and get to the decision point, and they end up somehow in this trap. So these guys are the starved. These guys here, let's see. These guys here are the ad lib 20% sucrose, and that is the nature of this behavioral phenomenon. That's the olfactometer in action. But here's where the real story is. What I want to do right now is to show you, with the best of science, how multiple cues can lead to the orientation of a mosquito in nature to a source of blood. So let's take away the lab. Bioassay begun. Take away the lab and bring us to the field. These are extraordinary studies. This is grand biology, in my opinion. And I want to show you kind of the way that this looks in nature. So in nature, let's suppose that we have, I'm going to use the word wind, but it really means it's a very small wind, not a mighty wind. This one is actually just a gentle breeze. Mosquitoes actually don't even go host seeking if the wind is too strong. They can't fly against it. So we have mosquitoes, or we have wind in nature, and then I'm going to draw here the host. So here is the unsuspecting outdoorsman. So we have all the things coming off of this individual that you would expect. And remember that wind is breeze is kind of a meandering phenomenon. Maybe little gusts and little diversions. So what's coming off of this individual, the first thing that's coming off is going to look kind of like this. We're going to have a streaky plume of odors coming off of this individual. So in black, what I'm going to show you here is what's called the odor space. So the odor space is basically being contributed by chemical odors. So this is all about chemo. And in this particular case, lactic acid, as previously mentioned, is a known chemical odor. And also octanol, a known chemical odor. As a matter of fact, they're exploiting this behavior right now. I mean, people have machines that you can buy at a Walmart or something to attract mosquitoes and kill them. And the lactic acid and octanol would be at least some of the chemical odors that are present. I'm going to change the color and show you that there's going to be a space kind of inside this where the mosquito could actually respond to CO2. This is the CO2 space. Now, why is the CO2 space not further out? Remember that CO2 is a normal solute in the air that we breathe. So if you remember our basic definitions, a solvent, which can apply to gaseous phenomena as well, gaseous solutions. A solvent is the major component. In the air we're breathing, it's nitrogen gas, right? 70-something% depending on where we are. Probably less as we go higher like we are here. And then the other things that are present in it, oxygen, carbon dioxide, and other gases, other small things in the air we're breathing, those things are solutes in the air. So CO2, it doesn't really stand out very much in a plume of odors that's coming off. Collectively, we call these two spaces, let's maybe use a different color to circle that. Collectively, we could call this whole thing kind of the odor plume. Odor plume. That's what that is. Keep in mind this is three-dimensional as well, so it's going to be traveling, away from the host, probably pretty close to land level. Could be rising, all sorts of things that are happening. So a mosquito's going to have to find this, and that's what I'm going to do next. And I'm liking this green color to be the flight path of our mosquito. So the first thing that our mosquito is going to do, here she is, wings out, flying. Looks more like a chubby mosquito. So here's our mosquito, and what she's doing is, for the first step of her behavior, is without detecting odor on these antennae, without detecting odor, when there's no molecules binding to the receptors here, she is going to be flying crosswind. So the first thing that our mosquito does is to fly crosswind. Gosh, I think I'm going to try to get a darker green on this thing. So crosswind flight. She's doing this. This is her general flight pattern. And then, upon reaching the odor space and having chemicals bind to her receptors, she will turn upwind. And of course, that's because she can. And the general flight pattern for a mosquito traveling upwind will be kind of a zigzag flight. I want to show you one very, very important thing. So number 2, she's going to turn upwind. More on this in a minute. And then number 3 here, this is a 180 degree. This is kind of a self-steered recovery turn. So I can call it a recovery turn. So it's a 180 degree turn that puts her back in the odor. So if a mosquito actually is stimulated and is flying upwind, but it loses that connectivity with those stimuli, turns 180 degrees, and a lot of times that'll bring them back into the plume. And then of course, we're adding, as we get into the CO2 space, more and more information with which to accurately kind of work your way up a plume. So now we've got this mosquito that is really making serious upwind kind of orientated flight to get to the host. I'm going to use red to signify kind of a temperature plume. So somewhere around the host here is going to be, especially, a lot of these Colorado evenings, they're a little bit cooler than they are in the humid eastern and southeastern United States. So a mosquito is going to be able to navigate, or excuse me, to orientate to the temperature as well. It's going to detect the temperature, and it's going to even be closer. And then at some point, this mosquito, at some point, there's going to actually be a visual space. So the mosquito could actually see. So this one here is visual. This one here is temperature. And basically, this mosquito is dead on. And of course, most mosquitoes feed on lower extremities, or at least a lot of them do. So that's why I drew the arrow down there. So there we have it. This is the whole story of orientation. Now, the most important part of this, from the Frankel and Gunn kind of thing, is out of everything on the board, what one term best describes this phenomenon? So think about it. What one of these variables? We have chemical odors, we have, oh, you know what else? I left one out. Can you believe that? Let's get this color. That should be blue. We left this one out too. This is humidity. So there we have it. We've got mosquitoes that have so many different things that they could use to orient to the host ultimately. So we have here chemicals. We have CO2, collectively the odor plume. Get closer, we have humidity, moisture coming off of the host. We have temperature, we have visual space. A lot of different cues that could be used. The most important cue, however, I've intentionally left standing up here at the top. It's the wind. That's the one that organizes everything else. And that's the one that gives us the name of mosquito host finding. So let's title this thing. Mosquito orientation to a host. And we're going to call this, I'm going to name it what it is. Also known as, this is important, anemotaxis. And I'm going to throw up here POS for positive. It's a positive anemotaxis. Mosquitoes are going towards the source. Wind, breeze, is the one that organizes everything else. So that's what we want to do when we start to talk about true orientation using multiple cues, is we want to kind of bring into the story that the best terminology that we have to describe the phenomenon. So mosquitoes use positive anemotaxis. There's a whole bunch of other cues, but we're not going to call it chemotaxis. We're not going to call it phototaxis. Mosquitoes are on the beat and finding you in nature long before they can see you. It's about the chemicals being encountered by the receptors, organized, however, by the wind. So that's how mosquitoes find a host. It's a very complicated process. Now, here's a good segue. I want us to think about this phenomenon in terms of all of the responses. They all are responding in a positive way to everything that's here. There's no negative, there's no cocktail of negative and positive. Where these mosquitoes go in this case is a whole set of positive responses. What we call multiple cues with which the organism responds in a similar fashion, ones that add up as they go to increase the ability to find it in this particular case, are concordant cues. All of these things. So everything here, as far as we can go, the cues involved, the cues here are concordant. This means that they're beneficial. They're all contributing in an additive way to the general behavioral response. Some animals are going to use mixtures of cues to end up being where they're going to be. It could be a combination, like I talked about for isopods, although this was not a taxis example, these were kineses, but I talked about a direct, so that's essentially positive, but a direct response to humidity in terms of the clino, and a negative response to light. So discordant cues there produce the ultimate stimulatory cocktail that renders the animal's position in nature. This one, all of them are together, we call these concordant cues. So I'm going to erase this board, throw the other word on it, and figure out what's next. It's pretty sad for me because I'm not going to be able to talk about mosquitoes for about 5 or 6 weeks. But I guess I'll get over it. We'll talk about some warm fuzzy things with nipples. All right. So, now we got to just kind of settle in on some straight definitions for this orientation. So, important kinds of concepts and terms. Orientation was the first one. I've been using that all day long. This is the way an organism positions itself in relation to external cues. Notice that we're using the word organism. And this is the class in animal behavior but there are other organisms that behave. It's not just an animal thing. Think protistans, not just protozoans like a paramecium or an amoeba, but think about an alga, some little photosynthetic flagellate or something like that. They all are orienting to cues too. So this is not exclusive to animals, this phenomenon that we've talked about. So the way an organism positions itself in relation to external cues. And that's important, external cues. Double underline there. That's orientation. The next one, navigation. Navigation is the process by which an animal uses various cues to determine its position in reference to a goal. The process by which an animal, and here I'm actually going to throw animal in, an animal uses various cues to position itself, to determine its position. In reference to a goal. There's a special little kind of add-in here, homing. So homing is round trip. So notice that I have emphasized over here, I've emphasized this goal concept, and homing is kind of a natural next step from this. So homing behavior is going to be round trip. That's what homing behavior is. So round trip with a fixed goal. So there's that goal concept again. The last one is migration. And migration is going to be the movement of organisms over long distances. Often in a seasonal manner. All right. So let's take a look at this presentation and put some direction to it. As a general rule, we're going to see complexity become more and more important. It's more complex. That means at all levels. More central nervous system machinery, more circuits, more sensors, the ability of modification, learning, plasticity. All of this stuff kind of increases as we go down the chart from simple orientations, navigation, homing, migration. What we're going to do at this particular point, the next lecture, is we are going to look at an extraordinary migrational phenomenon, and it's even beyond seasonal. We're talking a multi-year migration exhibited by, in our case, the loggerhead sea turtles. Sea turtles in the Pacific do it as well, but we're going to look at Atlantic loggerhead sea turtles and what they do from the time that they come out of the nest, so they dig out until they actually make it back as an adult, if they survive, to start their own parenthood. It's an extraordinary story, very, very well researched by a number of scientists across the globe, but most impressively to me is a couple that works out of the University of North Carolina. So this next lecture is going to be sea turtles, no more mosquitoes. All right.